Okay, it's your Stat Sensei back with some more homework help. So a machine process is established to produce metal wafers 2 centimeters thick. Uh, we wish to conduct a test to see if the new process mean is set correctly. 18 wafers are sampled and their thicknesses are measured. The results are listed below. From previous studies, it's known that the population follows a normal distribution and has a standard deviation of the population equal to 0.03. Because we have the standard deviation of the population, we know we're working with the Z. They're nice and tell us all conditions have been met. Then it says test at the 5% level of significance. Because they're saying a test, that tells me I'm running a hypothesis test. And because it's a Z and we're looking for a mean, I'm going to be using this formula. So test at the 5% to see if the machine is operating properly. Well, I need to define my parameter and let mu equal the true population mean wafer thickness. All right. Well, what wafer thickness did we want? Well, we assumed this to be 2 centimeters. We assumed it is working properly. So our null hypothesis is that the mean is 2 centimeters. All right. The alternative is our mean does not equal 2 centimeters. So I'm going to need to take a moment and enter all this data into my calculator. So I'm going to go to Stat Edit, and I'm going to enter it all into L1. All right. Okay. So once I have it in, I'm going to go Stat Test, and because it's a Z test, I'm going to highlight Z test, and I have data, so I need to input my data. So our data needs to be highlighted. My mean, my population mean is supposed to be 2. They tell me my standard deviation is 0.003. My data is in list L1, so I'll press second followed by the number 1. And what they ask for, they want to see if it's operating properly. That doesn't tell me that it needs to be too, it can't be too big, it can't be too small. So that means I need a not equal to, which is what I had. Oops. Stat test, Z test. Make sure I highlight not equal, like I have for my alternative. Okay, so now that I have this information, I'm going to go ahead and run this test, and we're going to start plugging into the formula. So I want the probability, I'm going to plug into this formula, that Z is less than, well, my X bar, the calculator just gave me that, is 2.0029, because we always go to the 4 decimal places, 2.0029 minus the claim mean of 2 over the standard deviation of the population, which is 0.003 divided by my sample size, which happened to be 18. Okay. And it was nice of them to tell me that the condition was met. We don't have to mess with a box plot, and they told me it came from a normal, so that was done. So we didn't have to do all the condition work. Now I need to be really careful here. This is a two-tailed test. Because this is a two-tailed test, I need to put a 2 times. All right. And so what we end up with is we ended up getting a Z score of 4.16, which is a pretty big Z score. So we have 2 times the probability that Z, and I wrote this the wrong direction. This should have said, because it's a positive, this should have been a greater than. So I should have made this a greater than symbol here. 2 times the probability that Z is greater than 4.1640 equals 0.0003 0.00003. Anytime we have 4 zeros, that means it's approximately 0. All right. And so we're going to take that p-value, our p-value, approximately 0, that's less than alpha, 0.05, we reject. So our conclusion, and I'm sorry that I didn't give you room for everything. Our conclusion is this. Our p-value is approximately 0. We reject the null. There is sufficient evidence at alpha equal 0.05 to suggest that the true population mean wafer thickness, because that's what we said up here, wafer thickness, is different, because not, and you could have said not equal to, is not equal to 2 centimeters or is different than 2 centimeters. Well, because it's different, we said that, we know the machine is not operating properly, all right? Or the machine appears to be not operating properly. So that's that. That's part A there. Part B, construct a 98% confidence interval and interpret the data. Well, we know our X bar, we already got that. When we ran that, we had 2.0029. Try to get that in a little better lighting. I don't know if that helped or not. So we have, and we're gonna go ahead and run this thing real quickly. Well, let's plug in what we have. So we have 2.0029. We don't know our Z star yet. Plus or minus, we'll leave a space for Z star. We know the standard deviation of the population was 0.003. So 0.003 divided by the square root of our sample size was 18. Well, I need to find my Z star. So I'm going to go second bars. Inverse norm. My area, parenthesis 1 minus 0.98, close parenthesis divided by 2, mean is 0, standard deviation of 1. And I end up getting 2.3263. And I'm not going to have a room for all that, so I'm going to write 2.326. All right. At that point, I've shown my work, and that's good. Please remember this is 98.98, and I'm looking for this X1 and this X2. This is our X bar, and our X bar happened to be that 2.0029. So we're going to go ahead and run this stat test. It was a Z interval because, and we were running it on data. Our standard deviation of our population is 0.003. Our list is an L1, and our confidence level is 0.98. And it gives us 2.0013 to 2.0046. So this is my interval. That's my lower bound, and this is my upper bound. Any value within that interval is considered a plausible value, all right? So we need to interpret our interval. We always have to do that. And so in this case, we are 98% confident that the true population mean wafer thickness lies in the interval 2.0013 to 2.0046. Now, if you remember, they wanted it to be 2 centimeters. And we noticed that 2 doesn't lie within an interval. So guess what? It's not working correctly. Matter of fact, 2 is over here. So it's producing wafers that are too thick. All right, so it's producing wafers that are too thick. If 2 had been in there, then we could say, you know what? We can't reject it. It's a plausible value. Because it's not in there, it's not plausible. So our interval once again confirms what we have above. All right, so medical research is testing a new drug to determine if it slows the growth of malignant tumors in rats. The average growth rate for this type of tumor in rats is 6.2 grams per week and follows a normal distribution with a standard deviation of 2.8. So they've given us a standard deviation of the population. This is what it does over and over again. So because they gave us this, we're going to be working with a Z. All right, and I want to know if it slows it. That's going to be important. We'll come back to that in a bit. So the new drug is tested on 30 rats. So here's my sample size with an average growth rate for the sample determined to be 4.1. So this is my X bar. So what we had before is this. 6.2, and then we got an X bar of 4.1. Run a hypothesis test at the 2% level of significance. Is its significance at alpha equal to 2% and at 1%? All conditions have been met. So our first thing, let mu equal the true population mean tumor growth rate. Well, that's positive. And our null, mu equals 6.2 grams. Our alternative is that it's slowing. It's less than 6.2 grams. We've written our formula down and we need to start plugging in. So we want the probability that Z is less than X bar of, where did it go, 4.1 minus the mean of 6.2, standard deviation of the population, 2.8, divided by the square root of our sample size, which we happen to have 30 rats. Okay, so there's my work. And notice, because it's only a one-tail test, I do not have to double this. Okay, I only double it if it's a two-tail test. So stat test, Z test, and this time we're working with statistics and not data. And our mean of the population was 6.2. Our standard deviation of the population was 2.8. Our X bar, we ended up with an X bar of 4.1, and we had a sample of size 30. We want to see if it's decreasing. We press calculate. So we want the probability that Z is less than negative 4.1079, which equals 0.00001, which is approximately 0. So our p-value is approximately 0. Our alpha, doesn't matter whether you use the 0.01 or the 0.02, but we'll just use the 0.02. It's less than, so our decision, reject the null. So then we're going to write that out. Our p-value is approximately 0. We reject the null. There is sufficient evidence at alpha equal 0.02 to suggest that the true population mean tumor growth rate is less than 6.2 grams. In other words, the tumor growth rate appears to be slowing. Now, technically, the question asked me to do it for 0.02 and 0.01, but in this case, either one we're going to be rejecting because we have a p-value of 0. So I'm not going to do it twice because I don't want to waste your time. So our p-value is approximately 0. We would reject the null. There is sufficient evidence at alpha equal 0.01 to suggest the true population mean tumor growth rate is less than 6.2. That's my interpretation. What does it mean? The tumor growth rate appears to be slowing. In other words, the medicine appears to be working. All right, thanks for watching, and I'll see you in the next homework video. Thank you.